All right, so today what we're going to do is finish up chapter 8. Now, as I announced earlier in the week, chapter 8 is actually not technically part of Calculus 1. So we're not going to be, you're not going to be tested on it, and you're not going to be expected to do any assignments from chapter 8. But having said that, I think it's very helpful that you've seen this material before you go into Calculus 2, because this is more or less where the course will start. So I want to wrap this up and make sure you have this background before you go on to back to school in the fall. So we'll cover that today, and then there'll be no more new videos. And just to reinforce what we said earlier in the week, all that's left for you to do this semester is the chapter 5 problems, which are due on the 21st, and then the final exam, and then that's it. So the final exam is just like the midterm. You'll be writing out your answers, handing them in. The class officially ends on the 29th, so that means make sure everything is done by then. And then I'll be posting all the grades in Heliotrope, but be aware that it sometimes can take a while before the grades are visible in your accounts. And also, if you're not a SUNY Purchase student, be aware that your account will expire, I don't know when, after the semester ends. So if you want to keep any of those notes, you might want to start downloading them now. Having said that, if you forget, well, it's not a problem. You can always write to me at my email address and I'll send you another copy. And also, if you need one, I can write letters of recommendation for anyone who's in this class, because, sometimes it's good to have a diversity of letters from different sources, especially with math. And so I'm available. Okay, just be aware of that. Anyway, so where we left off was we have several trig integrals to deal with here. And the problem with trig integrals is that there's so many cases that we need to think about that after a while we have to really maybe develop a small table of different situations we might run across because there's such a large number of them. Here's an example of what I mean. Imagine that we're now looking at integrals of not just sines and cosines, but products of them with different exponents. Okay, so whether the exponent is even or odd will determine what approach we're going to take. Now, we also should have access to ourselves tables that explain or list all the different trig identities that we might need. And sometimes you can find these on the internet, but the book has a very large table of them in the back. So why don't we go over there and find it? Yeah, you do find these too. And actually, these trig identities can be very helpful because often you may be able to take, for example, here, sine squared of theta. It turns out that it's also equal to 1/2 minus 1/2 cosine 2 theta, or equivalently 1 minus cosine 2 theta over 2. These are the some of the equivalent versions, which you'll find, but sometimes it may not be super obvious which ones you're supposed to use. And there's just a ton of potential identities with trig functions. So that's why it's important to have be able to classify these different techniques based on what's happening with the sine and the cosine. And then later on, we'll see what we do when we run across tangents. So anyway, I'll tell you what, let's just quickly open up the book. You'll recall that one of the appendices actually does contain a nice table of trig integrals, which you'll certainly want to lean on when you are doing any assignments in this material. Now, of course, if you are going on to Calc 2, there's a very high chance that you'll be using a different book. But whatever book you're using, believe me, it's got a table of trig integrals in the back somewhere. They all do. They have to. Okay. So this is a very popular book, but the chances of you're using it at your school are pretty low. And even if you're a SUNY Purchase, you might end up in a Calc 2 class with using a different book. So it doesn't really matter because this book covers all the first 3 calculus sections. And then in addition to that, it does have this table. That's pretty standard for calculus books. They usually go to cover the first 3 semesters of calculus. Calc 4 and beyond that are a little bit different. They're very specialized. Calc 4, or as it's sometimes called real analysis, is really more about proofs than actually solvents, or at least a large percentage of this, where they're diving down more deeply into the foundations of calculus. And that's where it starts to get really intense. Okay, so this is where we start to separate out pure math from applied math. If you're studying any form of applied math, you're not likely to go into that level real analysis because it's really meant for pure mathematicians who are going to spend their time proving theorems and developing new results. For people who might end up using this stuff for, let's say, financial applications or physics or whatever the case may be, um, there's really no point. Okay, I mean, it's nice to know you can prove things, but that's not the focus. All right, so I don't know, I must have clicked the wrong button here. Here we go. So Appendix B is a table, and a bunch of tables, and you can see the number of possible formulas you might run across is it's almost frightening to look at this. Okay, so but there are patterns that you might notice. And they do have to break it up. Typically, the approaches are different with sines and cosines versus the other trig functions. Okay, as you can see here. And then we have the arc sines and arc cosines and all the rest of the inverse trig functions down here. Um, and they've also very kindly put in here e to the u, log u, hyperbolics. We did not cover that. We're not going to. You may run across that in a different course, but they're here if you need them. So yes, there's a lot going on here. So we did some of these last time. So let's try a couple more. Um, so here's a general set of formulas where if you notice that it's AX, which means that could be any constant BX, cosine AX BX. And then you notice how we've got multiples of sine of one angle times the sine of another, the sine of one angle times the cosine of another angle. Down here, we have the cosine of two different angles. And they're showing us that we can rewrite these in several different ways, which once it's done like that, then it may become easier to integrate them. So, like I said, this takes a lot of practice. You really get some extreme practice, like constantly be working on these to notice them or recognize them when you see them. So, anyway, so what you're seeing here is a derivation of why these relationships hold. We don't need to focus on that right now. Let's just follow this procedure. And so what we have here is sine to the fourth of x. Now, if you notice, this is kind of, it looks like it doesn't belong in this category, but it does if you think of j of being 0, so that that cosine drops out. Okay, what are we supposed to do with this one? All right, well, let's see. We've got these two formulas, which we were just introduced to. I don't think they're listed here. These are just integration tables. There might be another chart in the book somewhere that has just trig identities. I didn't notice it, but it might be there. And if not, you can often find them on the internet. But you know what? Like I said, there's so many of them that it's possible that you'll find it very difficult. Oh, wait, here, I think this is what we're looking for. Yeah, because you notice here we have products of sine X, sine Y, et cetera, et cetera. So I think this is what we're looking for. And so what they're telling us is for something like this, sine squared is 1/2 minus 1/2 cosine 2x, and the cosine squared is 1/2 plus 1/2 cosine 2x. So what we're going to do is treat this as sine squared squared, which means this thing is squared. Okay. And when you multiply it all out, you ultimately end up with this. Okay. In other words, this, what you're seeing here is the equivalent of sine to the fourth power of x. So we're going to integrate this. Now, you might say, well, how does this help? Because these are a little bit more straightforward. So, for example, we break it up into three integrals as we've done so many times. And for the most part, we're going to move the constants outside just to make it simpler. Now, we can treat these individually. The first one is easy. Remember the integral of dx is simply x plus c. These are indefinite integrals, so we will need a constant at the end. Cosine 2x. Now that is a case for u substitution. Because if you notice, if this is our u, if you go back to our chart, you'll see that, oh my God, it's going to take a while to find it. There we go. The integral of cosine u du is sine u plus c. Now, of course, if u is 2x, we need du dx is 2, or du is 2 dx. But we don't have 2 dx, so we need to supply it ourselves. So if you notice, suddenly there's a 2 here and a 1/2. So we've supplied the 2 ourselves as we've done before. So we actually now have -1/4 cosine 2x times 2 dx. Or in other words, -1/4 integral cosine u du. Okay, so we know what to do with that now. So we end up with -1/4 sine 2x. Now, if you notice, we're not putting in the c. We're going to save that to the end. We've got 3 terms. We don't need a separate constant for each one. So we'll treat that separately at the end. So we know the first 2 terms. Okay, the first integral is x over 4, or 1/4 x. The second one is -1/4 sine 2x. The third one could be a little trickier, but remember, we do have these identities. That's what all this has been about. Cosine squared theta. Theta could be any angle, is 1/2 plus 1/2 cosine 2 theta. So we're going to write this as this identity. Okay, so this is let me just copy this here so you can see it. Just a quick reminder. So if you notice, this became 4x because it's 1/2 plus 1/2 cosine 2 times the original angle. The quarter has been moved outside here. So now here we have an integral that itself can be broken up into 2 pieces. And we'll go through that. A couple more constants to deal with. All right, so let's multiply through by the quarter. So we have 1/8 of the integral of dx, plus 1/4, because we have to multiply this by this term, of cosine 4x. Now, once again, guess what we have here? We need the 4. We're missing a 4. Okay. So we'll supply it here, and then we multiply the outside by 1/8. And so that third and final integral is 1/32 cosine 4x. So when you evaluate that, well, after all those steps, you ultimately end up with 1/32 sine 4x. So now we plug them in, we bring them together, and that's the final result. And then we add the c at the end. Okay. So in other words, bringing everything together that we've done, this is the final result. Wow. So that was a lot of work. But, along the way, we're repeatedly using the techniques we know up to this point. And if you go through it again, you'll see that at no point do we use any techniques we haven't seen before. But that's only because we were able to successfully reduce these messy expressions into something a little more down to earth that we could then apply our techniques to. So the challenge here is recognizing when to use these alternative versions of these same formulas. Like for example, here, um, how do you know that it's time to use this identity? Well, in general, when you have a product of cosines and sines, and you end up with a very messy result, there's a very real chance that you may use this technique because you no longer have exponents on your cosines here. Like I said, this is the kind of thing that only comes with practice. Um, you might be able to find a table that's listed where they're all together in one place, but you might want to put together one of your own. Now, this one is, it's just the straight ahead sine times cosine. So now remember, depending, we have it here too. This is one of those cases where we have a sine times the cosine of a different angle. And that would be this one right here, 1/2 sine of the sum. Let's use theirs. Where was that? Okay, we're looking at God, I lost my place. There it is. We need sine of one angle times the cosine of a different angle. That's the one in the middle. Okay, this one. Um, let me just quickly copy this so we can keep an eye on it. This is a special product called Snagit that you do have to pay for this thing, but once upon a time it actually came with Microsoft products. I don't know what happened to that. Um, Now you have to pay for it, but I find it to be incredibly easy to use, and that's all I need to know. All right, so okay, well, it was already, I just realized it's the same one that we have here, but that's okay. So in other words, you can see that this is our A and this is our B. So we're going to end up with 1/2 sine. 5 minus 3 is just 2x plus 1/2 sine, and then the sum of them is 8x. And then each one of these individually could be solved for with u substitution. Okay, so oh, and of course you'll want to factor out those 1/2s. Right. Yeah, 1/2 plus 1/2, right. So then we take the integrals individually. And now this one, in this case, u will be 2x. du is 2 dx. So we need to supply a 2 here. This one is u is 8x. So we now need to supply an 8. Okay. So we'll end up with it'll turn out to be 1/2 times 1/2. Okay. So we end up the first case, it's 1/4, as it says here, sine 2x dx, 2 dx. So we have so remember the integral of sine u, we'll go back to our book, is no, negative, don't forget that negative cosine u. So here we're going to have, since u is 2x, okay, or you can move the negative outside. So this is the first term. We're all set here. And, right, or it's written here as negative cosine 2x over 4. The second term, if you recall, is 1/16 sine 8x to 8. So here we have So then we'll have negative 1/16 sine 8x plus c for the second term. Oh, what did I do? Sorry. No, it's it's negative sine, negative cosine, my fault. Let's fix that. It's better. Okay. So now finally we can bring them together. And after all that work, this is our final result. So really, it's a two-step process. Number one, which case are we looking at? Are there any identities that can simplify the results? And once that part is done, the rest is actually straightforward because then you're just applying the integration techniques that we already know. So it's really more of a question of taking a horribly scary problem and splitting it up into smaller pieces or else simpler pieces or rewriting it in a simpler way. Um, Now you'll know you're going the wrong direction if you end up with something messier, but it's good to have these examples in front of you so you have a sense of what you should be doing. Now, oh, okay, so we save these for a separate case, because of course their behavior is very different, tangents and secants. Well, there's a lot of identities here. I mean, there's a lot of integration formulas, there's a lot of identities. They do not involve the sines and cosines. Okay. As far as derivatives are concerned, we actually saw these earlier in the course. The derivative of the tangent of x is the secant squared of x, and the derivative of the secant of x is the secant times the tangent of x. So again, just like what we saw before, here we're going to end up with all these cases where we have a product of secants and tangents. It's just a question of what is the exponent odd or even? That's really what we're focused on. All right. This is the case where we have secant raised to any arbitrary power and then the tangent. What do we do here? Well, let's see. All right. Well, here's one possibility. Secant to the fifth x tangent x. So we broke it up into secant to the fourth of x times the secant. Now, why did we do that? Well, let's see. What are we looking for? Here we go. Right there. The secant, the integral of secant tangent x is secant x. So in other words, this piece is easy to solve for. The secant to the fourth, well, maybe not so much, but there's probably an identity we can lean on for that one. Now, as we just saw, let's say that we decide that u is secant x in this case, but we're going to leave it like this. Okay, so in other words, we just got through showing that the derivative of the secant is secant x tangent x. So therefore, du is secant x tangent x dx. So what we actually have here is u to the fourth du. Oh, well, that was pretty straightforward. So we end up with u to the fifth over 5 plus c, and that's it. Oh my God, that was so easy. But, I mean, who would think, until you have had some practice with these types of problems, who would think to do something like this? Well, if you study these formulas, you might look at it and say, well, I'm looking for something that would make sense here. And you say, oh, wait a minute, look what I have here. So yeah, um, then you would see, but again, this comes with practice. Oh my God, look at this one. Now, remember, we did talk about these Pythagorean identities. The original one was sine squared x plus cosine squared x equals 1. And we can derive the rest of them from that relationship. So here we're going to need this one. Okay, it's one of the versions of the Pythagorean identity that involves secants and tangents. So how does that help? Hmm. Well, all right, here's what we're going to do. Those are, oh, okay, all three of them are here. And of course, this is the one that we'll need. So let's see, what can we do here? So the secant to the fourth is being rewritten as secant squared times secant squared because we can use this identity now. And you can see this one was turned into this. So how does that help? Well, let's multiply them out and see what happens. Oh, all right, maybe not. All right, let's try this. U is the tangent of x. Du, oh, and as we saw earlier, there it is. The derivative of tangent x is secant squared of x. So that's why this is here. Okay. So here's what we end up with. We're going to have du u to the sixth, 1 plus u squared. Well, then you multiply them out and you end up with u. Well, that doesn't look so bad because all you have to do is split it up now. You've got u to the sixth plus u to the eighth. And we know from the power rule how to integrate those. This is our old friend, the power rule for intervals. And so we end up with these two expressions. And then, of course, since u was defined as tangent x in the first place, this is our final result. Wow. um, see, but again, this is the whole thing right here. Once that's in place, the rest is pretty straightforward. Okay. Now, it's possible you might have tried something different and you would have ended up with something that was much messier than what you started out with, and that would be a sign that you should have tried something else. But um, at least you know that tangent times secant will often allow us to do something like this. So at least you have a sense of what could work. And now here, you notice how the cases get more and more specialized. Here, this is tangent times secant with different exponents, but what we're about to do only works if the tangent has an odd exponent. If it's even, we have to have a separate case. So what we want to do here is make sure that the tangent and the secant have even exponents. So we rewrite it to make sure that happens. So like here, for example, well, what do we do? Now we know that we want, our goal is to have even exponents. So we can rewrite this. Whoops, tangent to the fourth power of x. Oh, of course, it would help if we write down tangent x now. All right, so now remember, somewhere back here, we integrated secant x. Oh, wait, we just had it. Here we go. This is what, keep this one in mind while we're doing this. Okay. Well, it looks like we also took the secant cubed and wrote it as secant squared times secant, because whatever identity we end up invoking, the two exponents will need to be squared, or neither one should be squared. So we're going to take this one step further. Okay. So now we're getting into territory where possibly, now look what we did here. The tangent to the fourth is now tangent squared squared. Okay, so what do we do now? So it looks like we're going to rewrite one of those tangent squares in terms of secant squared. Okay. So it looks like we're making a bigger mess, but if we let u be the secant, let me just copy this so we don't lose it. Then this thing equals okay. And now you just multiply it out and you'll end up with a polynomial in terms of u. So, if you want to go through the steps, you can use FOIL on something like this, or now this is a technique that I've used in the past. If you could just multiply all the terms together. Okay, that's where this is coming from. Then you square it. You multiply them out. And once again, this is very straightforward. It's just a polynomial. So we can break it up into three integrals and use the power rule. And of course, remember originally we defined u to be the secant of x. So this is our final result. Wow. Oh my God. Um, that was tricky. Okay. But again, this part wasn't tricky. This is the tricky part. Breaking up the original using these Pythagorean identities and then choosing the correct u. That's the challenging part. Okay. Now, these two have other forms. Of course, there's always more formulas with trig functions. Look at this. Oh my God. So it doesn't look like this is helping us, does it? It seems to be making a bigger mess. But sometimes it actually might help. Same thing here. This is the integral of tangent x. So actually, this is good to know because if you had something like this, secant to the eighth power of x dx, you would then plug in all these numbers. You'd still have to solve this last integral, but still, it might make things simpler for you. Same thing here. So let's try this one. So let's go look at their identity, as they call it. So n in this case is, and so in other words, this is the integral of secant to the n power. And of course, that means n is 3. So we start making some substitutions. Okay, so here it is again when n is 3. So you see, if we plug in all the 3's, we end up with this. And this is very straightforward because we've already seen that the integral of secant x is, let's go back and find it. Way, way back here in the beginning. Here it is. Okay, so Now, this is not an integral. This is just secant times tangent. This is the part that we have to solve for. But you can see we've got the formula. So, and then that's it. We're done. So how was this? Okay. So for this one, we relied on these two. They're the so-called reduction formulas. And they're basically ways of taking a function. Now, you notice that we don't have the secant times the tangent or anything like that. It's just a secant raised to a particular exponent. Now, by the way, if the n is very small, if n is 1, we don't even need to bother with this, of course, because we have the formula. If n is 2, we may be able to replace it with the Pythagorean identity. But for 3 and up, that's when these things start to really come in handy. All right, let's try one with the tangent. So what's the formula for the tangent, the reduction formula, as it's called? Here we go. Okay, so n is 4. And now we end up down here. Now, what about this? Now, we don't have a formula for, or we didn't see an integral formula that just says tangent squared of x. It may be in the book. Let's see it. We've got the integral of tan. Oh, wait, there it is. Huh, that's interesting. Tan squared u du is minus u plus tan u plus c. But, oh, I see. So here we're using well, okay, we can use the reduction formula too. Although I think that makes it a little messier, but we're still learning about the reduction formula. So we do end up here. But the tangent squared of x, just write that down one more time. Tangent squared u dx was negative u plus tangent u c. So actually, that is the final result. You didn't really need the reduction formula here. You could have just taken it directly from this definition. And that's exactly what happened, as you can see here. Okay. Because here it's x, the u is x. Now, this part we don't have to go through. This is for your own benefit. This is just a proof of the Pythagorean identities. I think we may have even done this once before. But if you're wondering why these identities work, you can run through these. This is the main one. This is coming directly from the Pythagorean theorem. The others are derivations using the definitions. And here, this, I think I've already discussed this with you as well, how you can use this unit circle to find sines and cosines. For any angle you want. And then once you have the sines and cosines, then you can use the definitions to find tangents, cotangents, secants and cosecants. So we're going to skip over this. I think we're good here. Now, the last part has nothing to do with trigonometry. It's something that you'll find very, very helpful. And so this part that we're looking at is called partial fractions. And basically what you're doing is you're taking a polynomial of some kind and breaking it up, or actually a ratio, a rational function, I should say, of two polynomials, that is, and then you're breaking it up into component pieces that are simpler. Okay. The strategy being that each individual term might be simpler to integrate than the entire expression. So, but there's a special technique we need to make this work, and it's called partial fraction decomposition. For example, this function, this expression rather, is the same as this one. How do you know that? Well, that because we factored x squared minus x minus 2, or we applied, of course, the quadratic formula. These two mean the same thing. I think we can all agree on that. But what we didn't know is that we can now take it and write it like this, which you might say, why are we doing this? And then, of course, this means you have to solve for A and B, which you can do. It won't be difficult. It comes down to the idea of common denominators. So why don't we do this on a separate slide? And normally you wouldn't bother with something like this, but it can be helpful with integration. So here's what we have to do. So what I'm going to do is create a common denominator over here. Okay. Now, all of this implies that 3x equals a, x minus 2 plus b, x plus 1. And then we can do some algebra. And let's see, where does this take us? So now let's rewrite this. So we're going to write it. Just imagine on the left-hand side, we have 3x plus some constant, which is 0. So what we have here shows us that 3 equals a plus b. Coefficient of x is a plus b, which is 3. Then the constant is 0. So you have two equations and two unknowns. What we have here is simultaneous equations. Now, you can solve for these in different ways, including the so-called method of substitution. You can start with the bottom row. Note that 2a equals b. Second. Or you can rewrite this as a equals 1/2 b. Then on this side of the fence, which is the same thing as saying 3 times 2 over 3 equals b. Anyway, the bottom line here is 2 equals b. And if 2 equals b, that means that a equals 1. So what does that get us? So a is 1 and b is 2. Because let's go back here, and then all of a sudden, ooh, look what we have here. In other words, this expression is the same as this one. And now guess what I can do? I can integrate both sides. I think you'll agree. Now remember, we have something like this. Okay, so when you integrate a ratio like that, where you have a function of of x in the denominator, you'll end up with a logarithm. Okay. Okay, so here we're going to let u be x plus 1. Du is just simply dx, which means you have the integral of 1 over u du, which is log u, or log absolute x plus 1. Don't forget the absolute value. And then for the second term, we had 2 over x minus 2, same idea. We ultimately end up, oh, don't forget this 2, by the way. This gets moved to the outside. Okay, so this one is actually 2 log x minus 2. And then you bring them together, and this is your final result. So you may wonder, well, why did we use partial fractions? Wasn't there a way to do this directly? Well, I would say that that's possible, but there are other techniques we can apply here, but I think you'll agree this is not that difficult. It's just that it's a little time consuming. And so when you see a ratio like this of polynomials, often your first guess is that you should be using the so-called partial fractions. Okay. And this will start paying for itself when the expressions get messier and messier. That's when it really can come in handy. So I think there's one more example here. Oh, and here's an important detail. This is only going to work when the degree of the numerator is less than the denominator. Okay, now remember the word degree means the highest exponent in your expression. So in other words, the only reason we were able to do this is because this numerator is of degree 1, and this is of degree 2. Now you notice it said strictly less than. A tie doesn't count. Okay, then you would reduce it in a different way. If it was 2 and 2, for example, but because the numerator has a degree lower, strictly lower than the denominator, that means we can go ahead and use partial fractions unless we can think of something simpler, which is not impossible. It's possible that if we factor the numerator and the denominator out, we'll get some nice cancellations. Okay. All right. Now this is different because the numerator has the higher degree. So what do we do now? Well, there's one thing we can try. Long division. Oh my God. Do you remember how to do this? You're dividing x plus 1 into x squared plus 3x plus 5, and you end up with x plus 2 with a remainder of 3. And so you end up with this mess. But this is a mess that you can handle because you've got x, you've got 2, and you've got 3 over x plus 1. Clearly, this one will lead us to a log. By the way, let me take a step back here and remind you how this works, in case you've forgotten. Long division, you haven't done it in ages, but it works with ratios of polynomials, as well as integers. Now, we don't know if x plus 1 is a factor of x squared plus 3x plus 5. It might be. So the only way you can make sure is to try this long division approach. So I need something to multiply by x plus 1 to eliminate as many of these terms as I can. So let me try x. Now I'm going to subtract my result. If you notice, I multiply x by x plus 1 to get x squared plus x. I subtract those terms, and these drop out, and it would 2x. So let me try 2. I subtract, and I end up with 3. That's my remainder. So that means that this equals and you might say, well, what have we accomplished here? We made a bigger mess. No, now it's easier to integrate it because each of these terms individually is easy to integrate. Okay, we'll just use the power rule here and end up with x squared over 2. Here we just have 2x. And here we're going to wind up with a log. 3 log x plus 1 absolute plus c. And we are done. Oh my God. Oh yeah, so of course we're using u substitution, but so now this one has a numerator. In the numerator, the degree is 1. Here it's 3, and that's fine. Okay, we can still use partial fractions here. And so this is what it looks like. Oh my God. Now you can see here's the problem with this though. Suddenly we've got 3 factors in the denominator, which means we have 3 values to solve for. So that means we're going to have 3 equations and 3 unknowns. So if you go through all the common denominators like we did before, oh my God, look at all this. This is what it reduces to. But luckily for us, this tells me that a is -1. Plug it into the first 2 equations, and then we may be able to reduce one in terms of the other. And it turns out that 1 equals b plus c in the first remaining equation, and that 2 equals b minus 2c in the second equation. By the way, if you have been exposed to matrix algebra, you can use that to reduce the system as well. So, here's what you're going to do. We're going to rewrite this first equation as oh, I see what happened. The second one was rewritten. Oh no, this is the first one. Sorry. It's just rewritten as 1 minus c equals b, and then that's plugged into the second equation. There's many different ways you can do this. And then ultimately you do have your equation has just constants in the c. So you end up with c is -1/3 and b is 4/3. And so this is what we end up with. And now all 3 of these are going to involve logarithms based on u substitution. And here's our result. All right. Now, of course, we can combine multiple techniques. We often do. Okay, let's look at this one. Well, let's try u equals the sine of x. So therefore, du equals cosine x dx. Does that help? Let's see. Oh, it sure does, because look what happens. Right here, this can be, we can apply partial fractions right here. It's it's simpler than what we were doing. You have a over u plus b over u minus 1. Then we use our common denominators to find this result. And then we have 1 equals, well, let's write them out. And we have 2 results, 0 equals a plus b, 1 equals -a, and therefore b equals 1. So we make those substitutions. Now we're going to integrate, of course. And we ultimately end up with our final result. Okay, remember too that we define u to be sine of x. Okay, great. Now here's another specialized case, repeated linear factors. When the denominator has at least one term in the form of ax plus b to the n power. Like this one. Okay, you've got that square in there. We didn't have that before. What do we do now? Well, this part hasn't changed. But if you notice, this is the trick. We're not going to have just 2 terms, but we have to have 3. And you would think that We just break this up like this, and then that's what we'd see down here. But if you notice, this one is squared. That's the tricky part. With repeated factors like this, we have to have one term for each exponent. In other words, 2x minus 1, 2x minus 1 squared. If this was cubed, it would be 2x minus 1, 2x minus 1 squared, and 2x minus 1 cubed, and we'd have four terms altogether. But once we've established that, the rest is exactly the same. We use common denominators, and we end up, let me just show you at the end that we end up with, wow. We have u substitution. We start with 2x minus 1. The second one is 2x minus 1 as well. We also have x minus 1 in the third term. And so we're going to end up with a lot of logarithms. Not the second one, of course, but when you have du over u like that, that'll end up being a log. Oh, by the way, look what happened. We may have some cancellation here. So no, I guess not. But here, this is our final result. I think this is our next final technique, at least for this chapter. Oh, now that's a challenging one. What if we have in the denominator a quadratic formula which has no real solutions? Now, we know you can tell when that's going to happen by looking at the parabola. If the parabola doesn't actually cross the horizontal axis, that means what we have two solutions, but both of them are imaginary. Okay, you can tell just by looking at the parabola. If it doesn't cross the horizontal axis anywhere, then we'll have our usual two solutions, but they'll just both be imaginary. So then what do we do? All right, well, we break it up into two pieces, and suddenly x squared plus 1. Now, x squared plus 1, if you notice, oh my God, lands us into a lot of trouble. It ends up giving us, our solutions are plus and minus I. That's why we say this is irreducible. And if you notice, we can't simplify it. So we're going to proceed, as you can see here. And you notice what's changed. If we leave this squared in the numerator, it becomes ax plus b. Okay, we haven't seen that before. And then the rest of it is exactly the same. We're going to use common denominators, and you'll see that we end up with the correct result here. So all is saved. Okay, so anyway, so that's a lot of material. I know that, but like I said, when you get back to school in the fall, in Calc 2, you may even take a step further back and review some of the earlier material that we did, but this will be one of the earlier chapters that you'll be going over. You'll be spending a lot of time on integration. And luckily, though, in a class like that, you will be seeing some applications. Like, let's see what's coming up next. So basically, for all practical purposes, Calc 2 will probably start with 7. Okay. Infinite series is a very straightforward topic. It's actually quite interesting. And then after that, it'll start to really depend on what the focus of the class is on. But you're starting to look at, different dimensional shapes, and eventually that leads into Calc 3. Calc 3 is sometimes called multivariate calculus because you have functions of more than one variable at a time. In other words, y is not just a function of x. You might have something like z as a function of both x and y. And so it does get a little bit more complicated. So anyway, that's where you're going. Now, again, don't panic when you see this stuff. This is not going to be on your exam for this class, but I like the idea that you've seen it before. I hope it'll help you when you get to Calc 2. And, and little reminder too, you can have all these slides, but make sure you download them before your account expires, which I'm not sure how long that's going to be. The class runs out on the 29th, and they probably will have to give you at least a week, but if you do forget and you lose your notes, it's okay. I'll send you a new copy. Otherwise, I guess that'll have to do it. So right now, all you have to do is remember to finish the chapter 5 assignments. And then the final exam, you can you can send it to me as soon as it's ready. You don't have to wait till the 29th. And then I'll post the grades. And I don't know when they'll actually be visible to you, but if you're really desperate, I mean, you can send me an email and I'll write back to you when I have your grade. So I hope it doesn't take too long, but you never know. So anyway, I hope this was a good experience for you. Of course never had an online class when I was in school, and I'm not sure how I would have reacted to it, but that's how things are done these days. So I guess you're more used to it. And so I hope that this worked for you, that you had a good experience, that you learned a lot. And maybe I'll see you next summer. I mean, it's possible. They didn't offer Calc 2 this summer that I know of, but we may run it next summer in the same type of format. So anyway, so good luck to you all and hope you had a good time.